about this collapsing constructive and intuitionistic modal logics. So before I start everything, just to give the context, this constructive and intuitionistic are like the two of the major variants of non-classical modal logics. And from the title, you could probably imply that okay, in general, they're not gonna be they're gonna not gonna be the same. They're gonna be different. And yes, in general, they're very different. Sometimes very very different in like weird ways. But here I'll show one situation where they coincide. Um so before giving the definitions, I'll give the definitions of everything just to show like how different they can be. So these are intuitionistic modal logics. They have boxes and diamonds, and the constructive version of K and the intuitionistic version of K, Anupandas and Sonemari, show that they do not prove the same diamond-free formulas. To get from CK to IK, you add formulas. All the new formulas talk about diamonds, but this talking about diamonds allow you to prove new things talking without diamonds. This result, if not this example, appeared also, I think, on the PhD thesis of Griffey, but I think this was not published. This was the first place where it's published. And okay, so on K, you have these two very different variants of K. So say if you add the action B and look at the logic AB, say the logic of symmetric frames, actually the constructive and the intuitionistic versions of these two logics is going to be the same. And yes, I'll give all the definitions for you to be able to understand this. And first, uh, yeah, some definitions, quite a many definitions. I'm sorry, because yes, these things have taken time to define. Some motivating lemmas on the to give a more identity. Why does this theorem I'm proving should hold, even if these are not going to be the proof, but they give a feeling of why this is happening. And then I'll give a brief outline of the proof and conclude the talk. So yes, let's start with everything. So first, the logic CK. Our formulas are as generating modal logics. We have conjunction, disjunction, implication. We have boxes and diamonds. We have bottom here because it's convenient. And this logic CK, it's going to be the least set of formulas, which we put all the intuitionistic tautologies and these two variants of the action K. We have that box phi implies psi. From it, you get box phi implies box psi. This is just the standard K, but we also need this other variant to talk about the diamonds and boxes, their relation. That box phi implies psi, you get diamond psi implies diamond. Diamond phi implies diamond psi. These two things are equivalent classically, but not here. We can show that we actually need both of them. And taking these formulas, we get the closure under necessitation and modus ponens, as usual. And from this, we get a one logic. This, I think, was first defined by Mendler, the Paiva, based on another logic by Wijek with one more extraction. And this is like, this came more from like computer science point of view. So this is CK, we have two variants of K and necessitation modus ponens. So let's see how to define the other logics that we're gonna talk about on this talk. So we have the constructive version of KB, intuitionistic K, and intuitionistic KB. Now we add a lot more of axioms. First, we have these three axioms here. This the feature survey axiom that diamond phi implies box psi, then you get box phi implies psi. That we also get that diamonds distribute over disjunctions and not diamond bottom. Like it's not possible that something impossible happens. Uh, these three axioms are just equivalent. Classically, they're equivalent to K, but not on the constructive setting. And we put all these axioms together to get the logic IK. It's CK with these three axioms. And we also consider these two here classically equivalent, here non-equivalent versions of the B axiom. So from P you get box diamond P, and from diamond box P you get P. And yes, CKB you add the two B axioms to CK. IK you get by adding this non-equivalent uh, versions of K, and IKB you get by either adding the B axioms to IK, or you put the variance of K to CKB. This is just an equality in the like yes, and of course all of these are closed under both modus ponens and necessitation. So here we get the logic. So we have the basic logic. We can add some actions for symmetry related to symmetry or axiom variance of axiom K, and we get uh, a principle for probably maybe different logics, but not really. We'll see that these and these are the same. So okay, that's it for the logics, all Hilbert-Style axiomatizations. And now let's take a look at what we use for the models. All of the models of the logics are going to be based on the models for the CK, and we're just adding more conditions, so we get more restrictions. And here it's going to be more or less, you're going to combine a model of a Kripke model of intuitionistic logic and a Kripke model of modal logic, and put relations between them and see how it works. So, as is standard in Kripke models, we have a set of possible words, but here we also have a set of fallible words, which is going to be the sets where every proposition holds, including bottom. So you have like an inconsistent word or something like that. We have this relation, which I call the intuitionistic relation. It is reflexive and transitive, and it is essentially the intuitionistic relation is intuitionistic. You're adding information. We have a modal relation, which no restriction in this point, and some valuation. So like you from proposition symbols, you put a set of words where things hold. And restrictions we have if V has more information than W, then and W satisfies P, then V is also going to satisfy P. And for our proposition, it's going to be true on these fallible words, including the bottom proposition. And we also have that this set of fallible words is going to be closed under both of the relations. So if W is fallible and you can access V, then V is also fallible. Or if you can modally access it, then V is also going to be fallible. So it's essentially like this. We have this kind of so few closures, but it's the modal relation and the intuitionistic relation here are mostly unrelated. Before seeing on how to modify these models, let's take a little look at the valuations. So this is essentially the valuation for the intuitionistic model logics, which more conditions for the boxes and diamonds. Um, Essentially, a word is going to satisfy some proposition if and only if it is an evaluation we just get from the model. Some word can't satisfy bottom. It will satisfy bottom whenever it is fallible. So here we have that bottom may be satisfiable. It's going to satisfy conjunction if it satisfies both of the conjuncts, satisfies disjunction if satisfies one of them, as always. Implications, as in intuitionistic logic, if however you add more information, you have that phi holds, then psi also holds. So whenever adding information, you have the previous formula, you get the next one. The more interesting parts are going to be these two for the modal logics. So now we not only take the look at the modal relation, we're going to look at both the intuitionistic and the modal relation. So the box says that essentially, whenever you add information and go to another word, then phi holds. So box phi holds like however you can access with first going intuitionistic, then modally, then it's true. And the diamond means that whenever you add information, there is some U which satisfy which can be accessed from this new word V, and U satisfies phi. So it, like usually on intuitionistic first order logic, when you want to look at the existential quantifier, you don't need this to look up and then look to the next stage. But here you do need to do it. You cannot just look at one stage and then ignore it. So like there may be somewhere modally accessible which satisfies something, but this diamond of the thing does not hold in the word we have at the beginning. So the definitions are like this for the valuation. So now I want to define the IK model. So we had the CK models were like two relations and fallible words. And IK models are going to be like this. We have no fallible words, so bottom is not satisfiable anymore. And we put this stronger relation between the model and 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 intuitionistic relations. Uh, so the first one is forward and back as forward. Don't care much about the names. Just think about confluency. It will not matter much in this talk if you're not used to these things. So the first one says that if you can go somewhere modally and can go somewhere intuitionistically, you can get one confluence point. So if these two things hold, then there's a point where from here you can access intuitionistically and from here you can access modally. And you also have backward confluence, which means that if you can access someone modally and then access someone intuitionistically, then you can add information in some way that this new word is gonna be able to access modally this new one. And an IKB model, so these are IK models with these two conditions. An IKB model is just going to be an IK model where these relations here are asymmetric. Uh, we will see later why I don't define CKB models in a bit. But just as a side comment, uh, this forward confluence, when this holds, we can use the standard definition for the diamonds without having to look forward intuitionistically and find something. This is essentially because if you can find someone here which satisfies P, then oh, if this holds and you can find here locally, then when you go above, you can close this diagram and you find something which holds P. Yes. Just a bit, I forgot to comment, but all the monotonicity that if, say, if W goes to V and W satisfies some formula phi, then we get that V also satisfies phi. This is just an induction, but with this definition it works. And it's also why we need this condition for the diamonds. Without this, this wouldn't work for the CK models. So okay, we have CK models, no little relation between everything. We have the IK models, which you have more relation between the two, more connection between the two relations we have. And then we put symmetry to get IKB models. We get these three. We're going to think a little bit, mostly about the last one, but this is the class of models we're going to think today. And okay, with all the definitions, I can state precisely what is the main theorem and what is the proof. Essentially, we show that for any formula, these three are equivalent. So if CKB can prove some formula, by definition, IKB is just CKB with more formulas, then we can prove the formulas on the IKB. If we can prove something in IKB, then it's going to hold on all IKB models. This is more or less standard. You just need to check everything. I think this is even on the PhD thesis of Alex Simpson. We're not going to talk much about it today. And the interesting part is that if This holds in our model. We can use a canonical model argument to show that CKB can prove it. Uh, I'll go through the definition of this canonical model soon, after I give this a few motivating lemmas. So these lemmas are not enough to establish a theorem, but they give an intuition about why it holds. So the first thing is on IK models, we have these two types, forward and backward confluence. And if we add symmetry to a CK model, then we get that the relation is going to be forward confluent if and only if it is backward confluent. So with symmetry, this confluences coincide. Essentially, we had this like pictorial proof. We have one confluence that you have this, you can get this, and the other one is that you have this and you get this. But now if the relation is symmetric, we get things like this. And yes, flip, say, flip this one vertically, you get the confluence you have. Or flip this one and you get the other one. So if we have some confluence, we have both of the confluences. And now the other interesting part is, okay, we to talk about B, we need some amount of confluence because there's some CK model and word, which no need for this word here. CK model with a symmetric relation, but which fails to satisfy B. Essentially, this word here, it's going to satisfy P. We said we define the model like this. So W can access V, and only that, and from V you can add some information, and P works holds only at W. So okay, this is a CK model, nothing fallible or anything, and this is a symmetric relation, but B doesn't hold here. The thing is, P holds here, but this box diamond P does not hold because if box diamond P hold here, then here diamond P would hold. But box P works here, then P diamond P will work here. But then diamond P doesn't hold here because you can increase information some way where you cannot access anything which P satisfy. So okay, we need confluence. So the natural way of defining the minimal natural way of defining an IK model would be to have it symmetric, um, forward confluent, backward confluent. The only thing that would be lacking would be the non-existence of fallible words. But with the symmetry and the necessity of the fallible words being closed under the relations would just mean that we have an IKB model with a blob of fallible words which no other word can access. Or if it's accessed, it's only modal again. You can just cut it off and it's the same. That's intuition. And so this gives that the natural way of defining CKB models will be just the IKB models. This is still not completeness. And also relating to some other results in the literature, this also doesn't give completeness yet, but gives an intuition. It's let's have the orders. First, there's this theorem by de Groot-Schlitt and Glusson on a recent preprint that they characterize these three extractions they put on you need to add to CK to get IK, and essentially this points that the natural way of defining CKB models would, if we have the completeness, then we would have the equivalence. That this is still not the result, but it points towards to. And also, there's a paper by Arisaka with Das and Strasburger where they define a nested proof sequence for the model cube of constructive model logics and get some completeness with respect to the Hilbert style systems, no semantics. But one result that they get is that the constructive KB proves DP and proves N. They don't show that it proves the Fisher-Serre reaction, but they also don't show that it doesn't prove. So it's kind of yeah, what? So does if it holds the same, if not, it's different. And it's kind of like a points toward to these things being this IKB and CKB being the same, but still not the whole of the proof. So I'll give a short outline of the proof because it's essentially if you know canonical model arguments for intuitionistic modal logics, then it's that. But we use CKB and get some and can use B to prove some extra things, and it works. It should be good to comment that they're all different. It's in general more complicated to give canonical model arguments for constructive logics. We have to consider some extra structure, but here it won't be a problem. So we just use the intuitionistic one. So the idea is essentially like this. We're going to build words using a consistent CKB theories. CKB theory is just something containing all the CKB axioms and closed under model opponents. It is consistent. And if a disjunction is there, one of the disjuncts is there. So it's different from the classical model logics. We do not require a maximality, but we require some amount of closure. And the model is essentially this. CKB theories are the words, no fallible word because we're considering the consistent ones. A word can access another one if another one has more information. And the model relation is essentially what you expect it for the truth lemma to work. So you can go from gamma to delta if every box phi in gamma is in delta, and if every phi everything in delta is appears as a diamond in gamma. And for evaluations, we just look at the definitions. So sorry, this also shouldn't have been on one here. Forgot to erase it. So the first thing we show is that the CKB model is it's going to be an IKB model. We use the B diamonds, the B axioms to show that these models are going to be symmetric, and we also use it to show that the confluence can actually holds here, which is like the key proof of the lemma. It's a little. Um, sorry, Yanshilito says he can't hear me anymore. Is everything okay?
Yeah. All good.
Yeah.
Sorry.
Okay.
Okay. Everyone can hear, hopefully. So who cannot hear?
Yeah.
Okay.
Oh,
Yeah, continue, Leonardo, please continue.
okay, I'll continue. So, okay, we use the B axioms to show that the CKB model is an IKB model. This is the actual interesting part of the proof, but it's kind of annoying to show in a presentation, and it's just showing that okay, we have this kind of these words like this. Say you have from some gamma, you can go to some delta, not this, to some delta, and you can go to some sigma. Then you can build a word like this, and to show that the words are like this, it is reasonable to find a word like this. We use the B axiom like 2 or 3 times, and which is not accessible in say you're trying to look at the constructive version of S4 like or something like that. And this is a key part of using these extractions to get the confluences. And then you get the truth lemma that for all formula and all theory, then as the canonical model is going to set this theory is going to satisfy phi in the canonical model if and only if phi is in there. This is more or less standard. The more interesting part is here, but it's kind of annoying to it would be boring for people to just see a representation. So yeah, the trick is this. We show that the canonical model for the weaker logic is actually a model for the stronger logic. And from truth lemma, you get completeness. If CKB doesn't prove something, you extend it to a theory, and the theory in the model doesn't satisfy that, so IKB doesn't prove it, and you flip it, and you get the result. So yeah, well, in general, constructive and intuitionistic versions of the same model logic are not the same. We get the CKB and IKB prove the same formulas. They're the same thing. I mean, the intuition is that, okay, they shouldn't be the same, but yeah, they are the same. And from this, you get B. So you can just extend this for any logics which prove the action B. So one example, and this was actually the example where I found this result, is that the constructive version of S5 and the intuitionistic version of S5 are the same, as in they're the same logic. They prove the same things, which is funny because this IS5 is a very, very, very famous intuitionistic model logic. And it's kind of weird that nobody ever studied this. But yeah, people have studied this a lot because it's this. It's just that I never saw this written anywhere in the literature. And the way you, yes, and this is where I found everything. And this was a proof. I want to end it with an open problem. We got this completeness by restricting the frames to the symmetric ones, but this is not exactly the frame characterization. And it's kind of like, and also I forgot to comment, but the confluence was necessary for B box, but it's not necessary for B diamond. So we have all of these actions and duals from the model cube, and what would be the necessary and conditional sufficient conditions for the CQA frames to validate each of these things. There's a lot of work, but I think it would be I would be very happy to see this, and if nobody does, eventually I'll tackle it. Yes, and to close, yes, the main references. The slides are on my site, but everything is on this preprint. So if you want to see the details, you can just look at the preprint. It's same time title as a talk. So that was it. Uh, Thank you all.